And from next week, we will start new topic or chapter of the book. And before starting the lecture, I would like to share something. Okay, so usually in Easter break there is no lecture, and this year is the same. So there is no lecture in week 16 due to Easter break. However, we will not have lecture in week 17 as well because I'm not here. So I will create a doodle and put it in link with some other possibilities for scheduling an extra one. So please, later today, go and learn and in a doodle link and fill out the doodle. And hopefully next week we can pick a date or time for an extra lecture, okay? Then I will of course book a room for this extra lecture as well. And I will write everything in Learn, so you will have it there as well. So let's start with the brief review of what we talked about it last week. And here, this lecture, today is mostly solving examples. We have only, I think, 2 new slides and something which you don't know it now. But the rest are some examples. So last week I introduced periodic function, and you became familiar with the structure of the periodic function. And as you remember, the periodic functions are functions with the same pattern will be repeated for a specific period of time. So if, for instance, here you can have an example of a sine of t, which here you can see it has the period of 2 pi, and after that for each 2 pi you will have the same pattern as the first one. Of course, this is an example, it's well known. We are familiar with sine and cosine, but it can have different shapes. All periodic functions can be represented or can be written in a harmonic oscillation forms, which if we transfer or rewrite the signal in a harmonic oscillation form, we should use this format, and A is the amplitude, omega is the radian frequency, and phi is the initial phase of the signal. And of course, if you know the period of the function, you can use it to identify or find the basic ground frequency by using this equation, which is 2 pi over capital T, and capital T is the period of the function. So if you know the period, the omega can be found easily. Last week I also showed you that any periodic function can be written as this exponential form, the summation of Cn times this exponential. And Cn, as you know, is called the Fourier series coefficient, and we have a formula for it as well. This is an example which we solved it last week. I will not go through it today, but just to remind you that this function, as it is stated here, is a 4 periodic function. So capital T was 4. So we could find the omega easily, and then omega is here, which was pi over 2. And then always and always, the first step is using or finding the Fourier series coefficients. So we need to use the formula to obtain Cn. And if you remember, I mentioned that for Cn, we always consider 2 scenarios. If n is 0 and if n is not 0. If n is 0, it's a simple integration most of the time, so we can do it easily, even manually. And if n is not 0, usually it's much more complicated than C0 case, but it's possible to solve it and find the Cn coefficients. And here, at first, the Cn coefficients we obtained was a complex form, but as we discussed, it's possible to transfer real form as well, which was this one. Oh, sorry. Here, you can see it's not a complex form anymore. No problem. Now, let's look at the first example for today. For all of these examples, especially this one, I will give you few minutes time for each part, and then after you try yourself, I will solve it here. Okay? So you have a chance to try. So it says that consider two periodic function f of t, which has the shape of t square for the interval of -1 to 1. First, you need to plot the graph of f of t for three periods. It's up to you which. Is it both-sided periods or one-sided? And we need to specify the ground radian frequency. So now you have 4 minutes time to do it yourself, and then I do it here. And then when we are done, we go to the second, third, and fourth part. What is the period of the function in this example? What is capital T? Yes, 2. Thank you. So T is 2. And also, it's written here as it's there. Also, if you look at this interval, you can see that it's from -1 to 1. So if I want to plot it only for one period for now, and as you can see, it has the period of 2. So there's 2 units there. And now we have to plot it for 3 periods. It's up to you if you want to do all the plots in the right, left, or both sides. But here, if I want to do that, I go here. Yeah. So this is the shape. We also need to identify omega. How we do that? We have a formula, am I right? Yes, please?
2 pi over t.
Exactly. So 2 pi over capital T, which is 2, so it would be pi in this case. So if you see something like this in exam, and you could do this, then you got all points for the first part, which I think is it's not difficult. And for plot, you can use Maple, or MATLAB, or any other tool you have on your computer and you're comfortable with. So now let's look at part 2. Again, I will give you some time, but let's look at it for a second together. So we need to compute or write the function in a Fourier series format. So we need to write it in this So we need to write this in this format. In order to do that, first of all, we need to find Cn. contains Cn. So again, we consider two cases, N0 and N not 0. And then, when we have them, we can write it in this shape. Now you have 5 to 7 minutes time to try yourself. For the integration part, you are allowed to use maple, but because I'm a teacher, I have also the manual computation here, so if you are interested, I will go through the manual steps as well. But for integration parts, for now, I tell you, you can use maple. Okay, do you need few more minutes or more minutes? Okay, so few more, maybe 3 more minutes, and then we look at it together.
Yes. Jeg tænker også, når n er forskelligt fra 0, så kan man ikke ændre på formen. Så det er bare n for at sætte det ind. Den ender vel mere til alt efter ens mega. Så kan den bare lige lidt.
correct. But now you have to compute it for the range of minus 1 to 1. I think let's look at it together now. So first we consider, we go to Cn and we check, let's say for n equals to 0. Then of course we have to compute C0. We have a formula for it, so I just write that. It will become 1 over capital T integration over T of f of t e to the power of minus I n omega t dt. So capital T in this case is 2, so it will become 1 over 2. The integration over a period, which I select the first period, minus 1 to 1, and f of t in this range is t to the power of 2. Let's go here. So it is e to the power of minus I n, n is 0, I times, let's write it, I times 0 times, these are not convolution, it is multiplication, just keep in mind, times t dt, which e to the power of 0 is 1, so it will go away, this exponential. So it will become C0 is equals to half the integration of t to the power of 2 dt. It's not difficult. You can look at the tables. But I remember that it would be 3 to the power of 3 divided by 3. And I need to calculate it for the whole range of minus 1 to 1. So first, of course, I have this half. I put the upper limit here, minus, when I put the lower limit, which minus and minus is a plus, so I add this together. So 1 over 2 times 2 over 3. These 2 and 2 cancel out. So C0 would be 1 over 3. If you use Maple, you will get the same result as well. Any question for C0? Okay.
I have a question.
Sure.
How did you compute T over 3 times 3 and get the 1 over 3
Okay.
minus?
You know, the integration formula for t to the power of 2 dt, if you look at the integration table,
Yeah.
so I write it here. The integration of t to the power of
Is n plus 1?
n, let's see, x to the power of n dx. In general form, it would be x to the power of n plus 1 divided by n plus 1. This is the formula.
Yeah, it was
Okay.
not that question.
I mean, you are talking about this part.
No, talk when you take minus 1 to 1, how did you yes, sorry for interrupting.
No, it's fine.
Yeah.
Is it clear?
No.
You know, first I put 1 here.
Yeah.
And then 1 to the power of 3 is 1. Because it's 1 times 1 times 1.
Yeah,
So
yeah.
1 over 3.
Okay.
And then minus, always here it should be a minus.
Yes.
When you put the lower limit here. So minus 1 to the power of 3
Yeah.
is still minus 1.
Yes.
And now half multiplied by 2 over 3. These two cancel out, so the only remaining, or the answer, will be 1 over 3. Perfect.
Thank you.
You're welcome. Now, for a case when n is not 0, then Cn would be 1 over 2, the integral of minus 1 to 1, t to the power of 2, e to the power of minus I, n is the same, omega we know is pi, t dt. If you look at the integration tables, you cannot find the straight formula. At least I don't know. Maybe in some books they have it. I don't know it. But here I solved it manually. But as I said earlier, you can use methods, and usually in the exams which I designed in the last 4 years, I wrote that you can use method here. Don't worry about the exam. But now, this part, which is here in the middle, is the same as what I wrote there. Are you interested to see how this can be solved manually, or you don't want it?
Yes.
Perfect. Because if no one is interested, why we should spend time on it? In a case when we have something like this, we have a technique which we call it integration by part or partial integration, both names. So I write the integration by part. So we have a technique which is called integration by part. Here, we define or we rename some of the terms we have here. What we usually do, we take this exponential dt and we call it dv. So let's call dv as e to the power of minus I n pi t dt. So just I renamed it. And I call the remaining part, which is in this case t2, as a u. So now this integration can be written as integration of u dv. Why? Because I just renamed this as a u and this one as a dv. So if you want to use the integration by part technique, it says that when you have such an integration, the result would be always and always, let's say if it's from a to b, it would be u times v and compute it for the range of a to b minus integration of a to b of v du. I think here I haven't specified the range, but if you want, you can write the full formula as this one. Yes, please.
What is the straight line?
It means that first, when you have u and v, multiply them together, and then compute it for the range of a to b, like what we did. It is the same as if I write it in this way. We compute this for the range of minus 1 to 1. Maybe if it's better for you to understand, I can use the same way.
Perfect. Yes.
Less confusion, hopefully. So, if you want to do it manually, you have to do this, okay? Now, in order to do this, I need to know u, which I have it, because it's t to the power of 2. I also need to have v, but I don't have it now. I have dv. How can I obtain v from dv? Yes, please.
Integrate.
Exactly. So what we do now, because I need v, so from here I go this way. So v would be integration of dv, which in this case is the integration of this exponential, e to the power of minus I n pi t dt. Of course, the range is the same as before, but for now I don't want to compute it. I'll just do the integration. So it will become 1 over minus I n pi e to the power of minus I n pi t. Let me double check if I write everything correctly. Yes, that's correct. So now I have V as well. I can use the V here, but I need du as well. I have u. How can I get du from u? Yes, please.
Differentiate it.
Exactly. So du is, I write the differentiation of u. There is not a global notation, just the way I write it here. So I can write that du is the integration of u with respect to t. So it will become 2t. I mean du over dt is 2t. So from here, du would be 2t times dt. Because 2t times dt is the same as du. So now I have all necessary information such that I can use this orange formula. So I will use it. Cn, which was half of it should be u times v, and u is t to the power of 2 multiplied by v, and v is here, 1 over minus I n pi, I, e to the power of minus I n pi t for the range of minus 1 to 1, and then minus integral of minus 1 to 1 of v, again we have it, it's here, times du, which is 2t times dt, multiplied by 2t dt. Now, we need to compute this term and do this integration. So let's look at, do this one for now. First, I need to put 1 here, and then minus when we put the lower limit. However, are we agree that this 1 over minus 1, this term, 1 over minus I and p, can be factorization and come out? And then now I put t equals to 1 there. So 1 e to the power of minus I n pi minus, when I put minus 1 here, which is still 1, e to the power of I n pi, because it's a minus times minus. Is it clear? This is step.
No.
Which part?
The whole last part.
Okay, let me do it another way. No, don't worry, I will rewrite it again. So, again, let's put 1 here. It will become 1 times 1 over minus I n pi e to the power of minus I n pi. Are you agree with this? I just put 1 in t here and t here, nothing else.
Yes.
Okay? And then minus, when I want to put minus 1 here, minus 1 to the power of 2 is plus 1. This is the same, nothing will change. And here, this minus, with the minus 1, it will become plus 1. So e to the power of I. The only thing which I did maybe 1 minute ago was that I knew this would be repeated, so I had it out of the parentheses. What they are the same. So let's leave it with what is it for now. I think it's easier to follow now. Any other question for here? Yes, please.
I have a quick question about how you got 2t. I can't really figure it out.
Okay, you know, here I'm interested to find the derivative of u with respect to t.
Yes.
What is u? U is t to the power of 2.
Yes.
Now I want to take, again, let's do it this way. I want to take the derivative of t to the power of 2 with respect to t. Again, if you can't remember it, just Google or use the differentiation table. The derivative of t to the power of 2 with respect to t would be always and always 2 times t. This is how the derivative of this is defined. And now from here, because I'm interested to have du, only du, not du over dt, I said this can be written as 2t times the denominator I have here. So 2t times dt. And
Okay.
that's why.
Yes, that's very clear now.
Good.
Også F-mærke, det vil jeg selvfølgelig.
Hvad?
F-mærke.
Men jeg kan bare ikke forstå, hvorfor hun... Nå, okay.
Thank you.
Yeah.
Okay. Now I have to solve this integration. Are you agree that this term can come out of integration? Why? Because this is a term which is not dependent on integration variable t. So I can bring this out. Another thing which we can do is that I know I have a minus here as well. So I can multiply this minus by this. So this, now it will become plus 1 over I n pi integral of minus 1 to 1 of 2. Of course, 2 can also come out, so I will do it now. T times e to the power of minus I n pi t dt. Can all of you follow what I did here?
No.
No?
No.
Okay.
Actually, you have the back.
You know, this 1 over minus I n p is not dependent on t.
No, no.
And 2 is also not dependent on t. So I can bring those 2 and this term out of integration.
Yes.
If I want to do it as what is here, I should have a minus here as well. Am I right? Let's because I have a minus here.
Oh, you have,
right?
okay, yeah.
And this is a minus there as well. But minus times minus makes everything plus, and that's why I didn't have it first.
Ah, okay. But how isn't 2t related to t?
How 2t became t?
Yeah.
Okay, you know 2t, it means 2 times t.
Yeah.
And then 2 is a constant number.
Yeah.
So 2 can come out of integration, so I just
Okay.
brought it out.
Yes.
And
yes,
that's
yes,
why.
yes. Okay. Yes. Now. I'm
Good. Now, the bad news is that, again, you have to do this integration by part here again. Why? Because now I can define this as a u with the same dv. So I need to do these steps one more time. That's why I'm saying that Maple is good to use here. Because I think in one of the exercises you should do this 3 times. If you want to do it manually. Which I think I did it in the solution file manually. So now again, I use a different R. My new u is t. I need to have the u over dt, which will become 1. So du is dt. And dv is the same as before, so I can just write that. Minus I n pi t dt. And from here, v is 1 over minus I n pi t to the power of minus I n pi t. Am I right? I think so. Okay. Now, this is equal. Let's look at here. First of all, we know that we can make the factorization of these 2 terms. Also, let's see if we can use any of the Euler formulas we had last
2 over pi. So you can put pi in, and that's 1 or something. No.
Here, for now, let's look at only in this area, okay? In this area, first of all, I will multiply this minus by minus. So it will become plus, okay? And now, I make the factorization of 1 over I n pi. So I will only factorize the as a positive term. If I do the factorization of positive term, I can write it e to the power of I n pi minus e to the power of minus I n pi. And now you can see this. This is no. I want to use the top one for now.
Yeah.
I think I did the top one, but let me check my solution as well because maybe my brain. Yeah, it should be signed. Yes, yeah, it should be signed. So because we have this I here, you're right. So let's, if I want to use the sign, again we can, because we have, you can see I have this EIX minus e to the power of minus IX. The only term which I missed is 2, but it's okay.
This is just 2 times x.
No, because we also missed this half. You know, it should be it's equals to half big bracket for this, close the big bracket here, again equals to half. Nobody noticed that we missed the half here. And I close it there again. So here I have a half as well, which I can bring it down there. I multiplied by this one for now. Okay? And now I should have plus this half. This half, if we multiply by this one, it is 1 over I n pi. Why? Because the 2 down here will be cancelled out by 2 at the top. And now, again, we do the integration technique. I mean, partial integration technique here. Which, for that, again, another parenthesis. I have UB. Our U here is T, and V is minus okay. Let's see what I did so far. So, first, I multiplied this half with this one, and I made the factorization of this term. So, now I have 1 over 2 I n pi, and in the parentheses, I have some exponential term, which helps us to use this sign formula. Are you all agree with this part? Okay. Now, I have a half, which should also be multiplied by this, because this half is for this big bracket or parenthesis. So if we multiply, these 2 will by these two. So I have only 1 over I n pi. Again, another parenthesis here. And here, I use the same technique with the new u and dv. And then it will become uv for the range of -1 to 1 minus integration of v du. And the good thing is that here is just an integration of exponential. So from now on, we don't need to do this anymore. So let's simplify what we already wrote here. So Cn would be 1 over n pi sine of I n pi. Oh, n pi only. Sine of n pi. So this is equivalent to whole bracket we had it there. Because this divided by 2i is the same as sine of n pi based on the Euler formula. Yes, please.
You need bring down the board. Thank you.
Okay. Now I have 1 plus I n pi plus 1 over I n pi. Big parenthesis. Let's compute this. First, I put t equals to 1, so it is 1 over minus I n pi e to the power of minus I n pi minus, if we put minus 1 there, so minus 1 minus I n pi e to the power of plus I n pi. So this bracket is the same as this one. Then minus, why? Because, oh, not minus. Now, let's look at here if I did everything correctly.
There should not be two
It
minus.
shouldn't be a minus, it should be only minus here. Am I right? Okay. But minus times minus make it plus. So I can write as a plus here now. The plus, and also 1 over I n p can come out of integration. 1 over I n pi. And now, if I bring this out, so it's not here anymore. So I have the integration of exponential, and you can find it in tables, which would be 1 over minus I n pi e to the power of minus I n pi t for the range of minus 1 to 1. This is equals to. Any questions so far? Let's look at this part now then. What is the sign of NP?
0.
0, exactly. So no matter what is n, this term would be always 0. So 0 plus. Now, let's look at this part and see if we can use again any of this Euler formula. So of course, this should be also multiplied by here. So maybe I can do that first and then we do that. So it's, let's do it. I n pi, big parenthesis. I make the factorization of, if I want to use, I think cosine one here. Yeah, let's do it. Minus 1 over I n pi. So we should put the minus down here. E to the power of minus I n pi. Minus times minus 1 is a plus, and I make the factorization of this. So
didn't really see
Where is what?
where did you compute the interval from -1 to 1?
I haven't, for this, now whatever I wrote here is for this part. And here I don't have any -1 to 1.
No, down there.
I'm not done here yet. I haven't reached there.
Oh, you haven't reached it. Okay, yes.
No. This part, which I wrote it so far, is for this part. The multiplication of this with this bracket. Then plus, I should multiply this with this one as well, because this goes to this. Here. Yes. So it will become plus 1 over I to the power of 2 and 2 pi 2. And now I need to do the integration. I'm not integration, I mean put 1 and -1 there. Minus that's a lot of computation. Okay. Now let's simplify again. I do a multiplication, so it is -1 over I to the power of 2 and 2 pi 2 times e to the power of -I and pi or maybe I can also make the factorization of this and bring it out. I and I. Okay. What is I to the power of 2? -1, am I right? So -1 over -1 is +1. So it will become 1 over n2 pi 2 e to the power of -I and pi plus e to the power of I and pi plus here I have I to the power of 3 and 3 pi 3. What is I to the power of 3 is -I?
Yes.
I think so. So we have -I and so this is 1 over I and 3 pi 3. Well, because of this, and then e to the power of -I and pi plus e to the power of I and pi. Okay. Which is equal to. I have e to the power of -I and I. But I need to have a 2 down here. But I don't have it. Did we miss anything? I don't think so. No. So as you said, we should multiply by 2 and divide it by 2, such that we can get it. So I just write it here. So we multiply by 2 and divide it by 2. So it will become 2 over n2 pi 2, and then this would be cosine of n pi. Am I right? Am I right? Oh, it went to the standby mode. Sorry. Okay. And now for this one, can we use sine? E to the power of ix No, we should have a minus here. Am I right? We should have a minus there in order to use the sign. So what I do,
It's minus. Where did the minus go?
this is I to the power of 3, which is minus I. Am I right?
Yes.
But you
And then
have,
we had a minus down top here. That's
But-
why it became
But you
positive.
already have it in the brackets, the minus.
yeah.
Oh, you're right. So then it is a mistake here. Am I right?
Also the second.
It should be here. No, this one is from here. It should be positive. But here it should be negative. Oh, now it's good to go. I missed this one. That was a mistake. Small mistake. And now, in order to use I need again to have a 2 there. So again, I multiply this by 2 and divide it by 2. So it will become plus 2 over I p 3 or n3 pi n to the power of 3 pi to the power of 3 sine of n pi.
Sorry. Excuse me.
Yes.
You got the Oilers in the wrong order, so you have to get the minus out.
Oh, yeah, I can see what I was talking, because it should be plus minus, yeah. So if you make them, if you do that, then it should be a minus here. Am I right?
Yeah.
So maybe I move it down here. But anyway, the sine of n pi, as we know, is 0. So this part will become 0. So at the end, it is 2 over n2 pi 2 cosine of n pi. And we can write it as a minus 1 to the power of n. And that would be the answer for Cn formula if n is not 0. Yeah, that's why I don't write to use it manually or to solve it manually.
And n is always an integer.
N is always integer from minus infinity to plus infinity, and that's why we consider these two for them. Yeah.
That's not the result out yet.
No, it's-
type it in maple.
It should. Or maybe you need to do a small trick. Can I see your maple?
Yes.
First, you have not specified the range of integration. Just implement the integration and see if you get the same result. And let me know, okay? Any question? Still, we are not done with part 2 because we just got Cn and now we need to write it in this format. But before, because I need to have some space, just take a picture of the boards. And I promise when we are done with part 2, we go for a break. So just take a picture if you want. The solutions are also in a slide. Exactly the same solutions. Okay. I use the first board for now. And this is board number 4. So I erased part 1. So I can write f of t now as c0 plus the summation of n equals to minus infinity to infinity of when n is not 0 of cn e to the power of I n omega t. So it will become 1 over 3 plus the summation of Cn, which we got here, 2 over n2 pi 2, or I can write minus 1 to the power of n here as well. And then e to the power of I n omega is pi times t. And this is the last line of solution for, I think I have it somewhere here. Yes. But that I just wrote this out of integration, out of summation, but you can also have it in front. And that's the end of part 2. Any question? Did you get the same answer?
No, not het seems like
Så får vi nu nødt til at holde frem til termen, og så simplify, og så zoom ind.
Yeah. Perfect. Okay, if you don't